Today's class is being prepared January 11, 2021, and we have some snow here coming down. As we do class K is going to involve the Paulie equation, and we're going to play with spinors. And one cool thing with the spinors is that when we do a 360-degree turn, we don't get the exact same thing back. There's a phase thing involved. So Feynman has this cool way of a waiter to say go around 360 once and then go around 360 again, and then you got the exact same thing back. So you really have to go 360 and then 360. So look for that in the class. So we're going to do spinors in general direction and review some nice mathematics of spherical coordinates and integrate that with the matrices. That's a cool thing. And we'll also talk about the eigenvalue problem in quantum mechanics, that if you have the operator, the differential equation on the left side, it's going to get you the same thing back on the right with the energy for the time independent case. We'll talk about the meaning of that, talk about some measurement theory, and also talk about the Heisenberg uncertainty principle, another formulation of quantum mechanics. All very deep, good stuff. So I hope you enjoy the class. When we do the Paulie equation, by the way, that's putting in spin by hand, and we'll have to wait until the Dirac equation to see the beautiful, let's say, arising of the spin of the electron in a natural way. One more thing, we're going to be doing angular momentum, and we're going to show that the orbital angular momentum has a certain algebra, and it's the same algebra as our spinors with the Pauli matrices, the sigma x, sigma y, and sigma z, and that's going to make a connection to the existence of an intrinsic spin, the spin of the electron. So that's also very insightful. So a lot of deep stuff today. I hope you enjoyed the class. Chapter K. The Paulie equation. You can consider this as the intermediate step in our roadmap in going from the Schrodinger equation to eventually arrive at the Dirac equation in our travels. K1, measurement. If we look at the Schrodinger equation in one dimension, the time independent version, here's what we have. Notice that if we let this operator, capital H, be minus h bar squared over 2m, second derivative, plus potential, then we have an eigenvalue problem. When this operator operates on psi, you get the same thing back with the energy. And you're going to have a set, see the eigenvectors, and then eigenvalues that go with the eigenvectors. If you take a specific case with our particle going back and forth, say you take the third case, and here you can consider like the potential. Potential basically here is say x, going, this way from the origin, that the potential is 0 in here, and remember your force is minus the derivative potential energy dx. Then when you get here, say to the right, you have infinite slope, and the minus sign means infinite force to get you back. Here you have negative infinite slope. And then if you put a minus sign, it'll be a force that'll kick you back this way. So the particle is moving back and say back and forth like this. You know, it's basically going to hit here and then come back and hit there, hit there, and hit there. So here, this third case, you know, 3 halfways for the third case equals L. And remember, the K is 2 pi over lambda. So K3 would be 2 pi over lambda 3 here. This is lambda 3 is going to be 2L over 3. So 2L over 3. This is going to come out. 3 is going to come upstairs. 3 pi. 2's cancel over L. And our function here is going to be some amplitude times the sine K3x. And there was a cosine term there, which we're doing a time independent case, so we don't worry about that. Or that would be, you know, an e to the minus, you know, I omega t kind of thing. We don't need to worry about that. We just have the spatial one here. So then if you take the derivative of this thing, you're going to get c minus h bar squared root 2m. The derivative here is going to be equal to the e times the function. So you get the same thing back. The minus signs will cancel, and you'll find that here, like this second derivative will be a minus K3 squared, and you get the same thing back. So here, this is then going to be a minus K3 squared, get the same thing back. So that means h bar squared K3 squared over 2m is equal to the third energy level. So to find E3, we want to take the K3 here and put that in there. We need to square it. So we'll have the h bar squared, and when we square the K3, this will be a 9 pi squared, and then there'll be a 2m and then an L squared. Now, if you remember, we did the energy levels and it had the general formula, n squared pi squared h bar squared over 2m L squared. So looking at these two here, you see if the n is 3, you'll get the 9, and you'll have the pi squared and the h bar squared. So you can think of this as taking a measurement. If you have, for example, the third state and you apply the Hamiltonian on it, you'll get the energy of the third state, and the third state will come right back. It'll be that you won't disturb it. So here, you'll get then this eigenvalue, the third energy level. So that's a nice way of looking at the Schrodinger equation as an operator equation. You operate with the Hamiltonian on an eigenstate. You get the eigenstate back plus the eigenvalue for that eigenstate. And your general case will be these eigenvalues here coming from the energy levels. You can think of what we did here as sort of making a measurement too. The sigma z on 1, 0, 1, 0, 0, minus 1 from the last class here. This is going to get you the 1, 0. We did this last class, and here the eigenvalue is 1. You get the same thing back, and you get the measurement. Now we're going to define the spin operator
to be h bar over 2, and we'll understand this better as we go, because in this case, you'll get the same thing back with h bar over 2, and you might recall, like chemistry, spin 1/2 electrons, a spin 1/2 particle, all right? So we'll come back to that. So say in general, you have an operator, measurement operator A, you operate on a state, and you get the same thing back with this eigenvalue. And suppose if you make a different measurement, B, and has a different eigenvalue, but you get the same thing back, like the same thing back. So that means if you take these two, one after the other, you would get here, you know, the B, this second, you know, this is the latter part. And then when you pull out the B as just a regular number, then you would get here B, this would be A times S, you would get this. And if you flip them, you would simply get the same thing. This would be flipped. And since A times B is B times A, then like the eigenvalues, then you could say, you know, AB minus BA working on here is going to give me, you know, the AB, it's basically going to give you, you know, BA minus AB. It's going to be 0. So we say that these operators commute, that you can make measurements, you know, 2 different measurements, and have eigenvalues, like those 2 simultaneous eigenvalues. So you're going to have some cases where you can't have this. For example, if you take the sigma x1, which is 0, 1, 1, 0, onto 1, 0. This, turn that sideways, get 0, turn that sideways, get 1. See, that's not the same thing. You don't get the same thing back. So see, we looked at the eigen vectors for this, and it was, you know, something like where you had, you know, 1, 1, you had this, you know, or you had, say, with the -1 there. So some operators are not going to be like compatible with other operators. So see, if you did the measurement on this thing, you would get, you know, if you, with the Z, say, if you did that, you would get here the same thing with the minus sign. So in other words, making the measurement of Z with respect to this thing would give you the +1 eigenvalue, but then if you operate with this measurement, change the state, and now do the measurement, you get something different. You get the -1. So that means that these, see, are not going to commute, and you already know this from the other class. If you take these 2 together, let's go ahead and review that. And just go ahead and flip the order. See, this one here is going to get you a 0 there and a -1 there. This one here sideways gets you a 1, sideways gets you a 0. This one sideways there gets you a 0. This one sideways there gets you a 1. Sideways there gets you a -1. Sideways there gets you a 0. So when you put the minus sign in, it's the same as this, and we already know this. You get 2 of these, where if you put the I here, then you would have, say, a minus I there. I would have this, and that is the Y1. Now let's look at this. If you have XZ and minus 2I sigma y. We said if these were cyclic, you would get this kind of thing with a plus sign, but see, they're not cyclic. X, this is not y. So that's why it's a minus sign. If you had this one, say, or put the z first, and then the x one second, then you would have a plus, because see, now you have x, y, z, you have cyclic. So in other words, the fact that these don't commute, you can't have the simultaneous eigenvalue like you can up in here. So let's summarize these from the last chapter. We found that if you have the commutator of these, you get 2i, the permutation symbol here, J, K, L, and the sigma L. So the operators don't commute. So you need to consider that. In other words, you could say that when you take the measurement, if you take the Z one with these, they don't change these, they're eigenstates. But if you take, say, the X one, you basically took this thing and you like changed it. You got something else. We got this, we knocked it down, say. So you changed the state. And that brings us to the uncertainty principle. Heisenberg's uncertainty principle here, where you can when you take a measurement, you may disturb a state, or you may not. If it's an eigenvector, you get the same thing back. So we have to consider the general case. You can disturb the state. So what we're going to do here is in one dimension, we're just going to have here just the derivative here. So this is one dimensional case. And now what we're going to do is take a measurement, and with x, the operator, for example, v of x was just v of x. So if you want to use x as an operator, and then p as an operator, you're going to be using this. Operate on some wave function like this, you'll have x times minus I h bar d dx, working on some wave function. And this will give you here minus I h bar can be pulled out, constant, and then x times this derivative. But now watch what happens if we operate the other way. In other words, we put the x first, and then we take the measurement with the momentum. Then we have minus I h bar d dx, working on x psi. Now we're going to be using the product rule. So this is minus I h bar, take the derivative of the first one, is going to be a 1, and you'll get this. And then if you take the derivative of the second one, you'll have that. And now the thing is, if you subtract them, if you take the x with the p, in that order first, and then subtract this one where you have the p second and the x1 working on it first, you would be taking this one, top one, subtract this one. So we have this subtraction. Let's see what's going to happen here. This will cancel this. And then you'll have minus this. So you'll have an I h bar psi, subtracting the bottom one from the top one, which is what we're doing here. So you're going to get minus this. So you can now write this as an operator equation, that the commutator of the x and the p is equal to I h bar. And the fact that this does not give you 0, you cannot have simultaneously eigenvalues for the position and the momentum at the same time. So you can't do that. Because you're basically going to have the change of state effect. You're going to disturb the system. And that's the uncertainty relation. So what we should do here is put a little title in this section here And let's just say that this analysis here, let's go ahead and put it maybe up here, K2 somewhere, a Heisenberg uncertainty relation, with this little analysis here. So you can think of two formulations of quantum mechanics. The Schrodinger picture, which would be the Schrodinger equation, here's the time-independent version of one dimension, and Heisenberg's picture, or the Heisenberg picture, which you can write as an operator form with this kind of an equation where the x and the p do not commute. And there's more, there's more here that you can write than the h, for example, as an operator. You think of it as an operator, and then this is the Schrodinger equation. Here we got Max Born, we should mention, because he gave interpretation of the wave function, where if you take the wave function complex conjugate, multiply it by the wave function psi star psi, you get the probability distribution, where this gives you the probability of finding a particle between x and x plus dx. Nobel Prizes were awarded to these three individuals, Heisenberg in 32, Schrodinger in 33, and Born in 54, for their work in quantum mechanics. Max Born's also grandpa to Olivia Newton-John. A little more detail on the prizes. Schrodinger shared his prize with Dirac, and Born shared his with another scientist that was honored for work in physics. K3, angular momentum. Now, the angular momentum, the definition, if you have a circular orbit where you have r, and here you have mv, which is your p, the definition is to take here and multiply these together. This is mvr. This is your angular momentum in classical physics. And if you're looking at something that's traveling, to say, at some angle, you really want the component that is going to get you the perpendicular with the moment arm. And that's how, when they have a force, that's how they define torque. But let's just go ahead and just define this formally like this. This is an r cross p. So here's your r vector. And if that's your momentum vector going this way, then here's the momentum vector. Here is the r vector, and there's your angle. So if you take r cross p, you'll come then, your thumb will come up out of the page, and they'll have a direction associated based on the cross product. So this is the definition of angular momentum, and we would like to figure it out. So we'll use the determinant form for the cross product. So this is x, y, z, that's your r vector, going to be in this one, and then the p for down here will be px, py, and pz. So when we work this out, we're going to get here I hat, that'll be then, these get multiplied, y times pz, and then these get multiplied, minus the z py. Then a minus j hat goes in next. Then we have x with the pz minus z with the px, like that. And then finally we have the k1, which should be x with py minus y with px. Now, since these are all different, like y and z and all that, the order doesn't really matter, because your px, for example, is going to be equal to minus I h bar, d dx. Probably should go ahead with, could just put a partial there since there's more stuff going on here. And here, this is z, so z and x, see, so the p's are derivatives. And then you have the coordinates, these are never the same, see y and z, z and y, x and pz, so therefore it really doesn't matter because these are independent variables. So this would be L, the x component, and the y component would be, put the minus sign in, z px minus x pz, and this would be the z component. So what we would like to do now is take the commutator of Lx with Ly. And that means we put the Lx one in here, which is y pz minus z py. And then we put in the y one, which is this one, z px minus x pz. And now I will be careful with order because see, when z, there's z's here when these come together, so you gotta be careful here. So this is gonna get me this commutator. I'm gonna have 4 commutators. I'm just gonna copy them down. This is the first one here. This one's gonna work with this one over here. All right, like that. So that's that one, say that one over there. Then there'll be a minus, and then there'll be here, let's go ahead and let's do this one for both of these first. So that's y, p, z, and the minus sign's coming from here. And then I would have x, p, z. Then work on this next one. This is z, p, y, working with z, p, x. And then the last one, 2 minus signs will cancel. I got a plus z, p, y, it's this one. And then this last one, x, p, z, all right? So like we put this one here, and we put that one there. And then we have this one there, and then we have that one there. Let's see, the minus sign came with that. Then for here, we have this one here with the minus sign, and we have that one there. Then the 2 minus signs cancel, we get a plus sign, we have this one there, and that one over there. Now here, we can factor out everything except the z stuff, all right? Because there's 2 z's in there, so we can bring this out, have this, and then we can take out here the y and the x, and then have the pz's. And then here we can take out the py and the px, and have the z with the z. And then the last one is the x and the py. Now, an operator with itself is going to commute, the same thing. It's like pz squared minus bz squared. And this is going to be z squared minus z squared. So that's going to be, like this is going to be z minus zz, same thing. So they're going. Now here, remember, we have the relation with the x and the p, and I'll put a little px there, is IH bar, and you're going to have this with all 3. So that means this one, which has the different order, is going to be a minus IH bar, because in other words, the z, pz, will also have this relationship. And then over here, this one, oh, we have a mistake here. We have a mistake here. We pull the p, this is actually a z. It's easy to make mistakes, and I kind of prefer making mistakes as I go because that's what really happens in life, rather than copy my notes precisely, correctly. I mean, the book's got that, so you can read that in the book, but I think it's good to work things out make some mistakes and then like fix them. So this one here is I H bar. So that means the Lx and the Ly, like this, will be here. You can factor out the IH bar. Then what do we have? We have the X with the PY, and then the other one over here, we have a minus sign, and then we have the Y with the PX. But if you look at this thing and compare it with here, you can see that this says the LZ. So we have a very profound discovery here, that there is this cyclic relationship XYZ with the angular momentum. And this angular momentum, just to emphasize, is orbital. Orbital angular momentum. Now you might ask, why did I do this? Well, the big payoff's about to come. Now, if you were to go ahead and do all three of these, where you have, say, some J, where this is X, Y, or Z, or 1, 2, 3, and this is, say, K, you would find you would get IH bar, and you would get this permutation coefficient here, and then you would get this. But now comes the big payoff. Now, where's this big payoff? Well, this expression for the orbital angular momentum looks very, very close to the relationship we found with the Pauli matrices. We found here 2I, and then the permutation factor, and then we had this. Very, very close. Can we make this bottom one look the same? We need to get an H bar in here somewhere, and we need to have a 2 go away. Well, let me write out what this commutator is in detail so we can see precisely what that left-hand side is. First, let's consider the 2. If we get rid of the 2 by dividing by 2, we got to divide by 2 on this side. But where would the 2 go? Well, here's one way we can do it. We can divide by 4 so that we're dividing each of the sigmas on the left-hand side by 2, and that's a total of dividing by 4. And then over here, we're dividing by 4, and notice that this is very elegant, that all these are going to be looking the same. But now what about the H bar? Well, if you stick an H bar in here, then you would need an H bar on the left side, but we got two things here, and you might think that I put a square root of H here, a square root of H there. I'm going to show you why you don't want to do that. And what you really want to do is put H bars in front of these sigmas. If you put the H bars in front of the sigmas, then you have an H bar squared, an H bar squared, and here you have an H bar squared. Now the reason why we want to do that, I'm going to show you that the dimensions of angular momentum, which would be the dimensions of R cross P, going to be the dimensions of here meters times, remember that this is your kilograms, is your mass times your speed. So this is kilograms meters per second. And if I take the kilograms meters per second squared and put a second there to cancel, and then have an extra meter floating around, I got meters squared bounces now because I have that extra one over there. Meters squared, and 1 over second, a kilogram. See, this is mass times acceleration, so that's newtons. And then here, I'm going to put this m first and put the s over here. This is force times distance. This is work, so that's joules. So your units here are joules times seconds for your angular momentum. And if you were to look at the prescription that we did here, where we had r cross the minus I h bar, the del consists of like derivatives, so that's 1 over meters. This is meters, that cancels, and you get h bar. So the dimensions of angular momentum are h bar, and let me show you that h bar has units of joule seconds. If you look at our formula that we did earlier, say the energy is h times f, or h bar omega, then this gets you joules. Now, usually when you write out the joules, you put here a lowercase, and then if you abbreviate, we do capital. So that's joules. So here, if you just look at, say, we can do the h bar omega 1, doesn't matter. So this is going to get you joules. Say we have h bar units, and this is radians per second. Radians, they're dimensionless, so this is per second, and that would be the same thing if you did this one. You would have per second. So it doesn't matter. H bar has the same units as h because you're dividing by 2 pi. And what do you got here? You bring the seconds over there. You got joules times seconds. That's it. Joule times seconds. That's what you want. Joule times seconds, which is what h bar is also what your angular momentum is. Okay? So here is angular momentum units, joules times seconds. Here is h bar, or h units, joule times seconds. So they're the same. So therefore this justifies what we're doing there. Then we can now write then the Sj as h bar over 2 sigma j, or you can write this as a vector, and then you have here a vector on the right hand side for the Pauli matrices x, y, and z. Then, see, this is now going to be, if you put the j for the s, and say here the k, now the 2's go away. See there, you got the I, and this h bar will be in there. Then you'll have the permutation coefficient, and then here you'll have the SL. And now this equation here, this commutator, looks precisely like the one up here, where you've just taken the symbol L and replaced it with S. Wow, same algebra. So that means this has to be an angular momentum. That's what's suggested, say, by the mathematics. And we call this the intrinsic angular momentum, while this one's orbital. And this one here, remember, we had states like this, the eigenstates like this, which we can call spin up. And we had spin down like that. So the actual factor in front, h bar over 2, we sometimes refer to as that 1/2, saying that the electron is a spin 1/2 particle, because the half shows up in terms of h bar over 2, for example. While when you had the angular momentum here,
the operator here has an h bar. So we have the same algebra with the S's as we do with the L's. Orbital and intrinsic spin. Fascinating. So the total angular momentum J would be the orbital plus the spin. And now you can see things like this from like chemistry where you learn about the spin of the electron. K4, general spin eigenstates. What I would like to do now is to consider coordinate system. Say here is your x-axis, here is your y, here is your z. And you know, this is very popular in physics classes to do the spherical coordinates. This is your origin here, and this is the angle phi. Now in math class they may have different angles, but that's okay. This is rho, this distance here. And this is r to get you up to the point, say P in question. And the unit vector points along, say this, sometimes they just use r hat, points along this direction. And we would like to pick that direction and then have our discussion with spin. Now, remember that when we write down the spin up as a 1 and a 0 like this, and the spin down as a 0 to 1, these are the eigenstates for the z case. All right, because the z operator, you know, has this feature. Now, I'm going to leave the h bar over 2 off and just use this more the pure math version. So what would be if we had one of these up and down, what would it be if we measured along some angle C? So let's go ahead and look at this. So the n hat is equal to the r hat. And here, just to remind you here what's going on, that if you look at the r first, let's just do r first. If you look at r, you have x, you have y, and you have z. And so before we write this down, let's just note that the z, this is the z, that's r. If you make a door here, that's kind of cool to see the door like that, and this rho is up there. But if you take the r and go with the cosine, you get that z. So this is r cosine of theta. To get the rho, you want r times the sine of theta. R times the sine of theta gets you that rho. Then if you want the x coming out of the rho, you want the rho times the cosine of phi. And then for the y, you want the rho times the sine of phi. So this is going to be r here, sine of theta, cosine of phi. Now, hopefully you've already seen this more than once. And this is going to be r sine of theta, sine of phi. All right, so there's your phi. So rho times the cosine gets you x. And so this is your rho. So you're working with rho here. And then rho times the sine will get you, actually, if you want to, the y would be this thing here. So that's your rho times the sine. So when you want the unit vector, you divide by r, because you want the unit vector,
is going to be without the r, it's a unit length, so we need sine of theta. We just copy now, cosine of phi I hat plus sine of theta sine of phi. This is a nice exercise to review things from math class. Now if I take the n and dot it with the sigma, where the sigma are the Pauli matrices, I would have here so you can think of this as sigma x I hat plus sigma y j hat plus sigma z k hat. So I dot I would be 1, and I would have this times whatever that is, which is 0, 1, 1, 0, like this. And then the next one here, this would be the sigma y1, which from the other class we know is this. And the last one, the cosine of theta, with sigma z is 1, 0, 0, minus 1. So now we can write this nice little combination of your spherical coordinates with your Pauli, nice, and your r hat vector. So if we do all this, let's think what we get here. Get some kind of cool stuff. Up in this left-hand corner, we get nothing from here. We get nothing from there. We just get the cosine of theta. Then in the right-hand upper, we're going to get here, this is going to kick in. So we're going to have this, and we're going to have this, and there's going to be here a minus I. So that means we're going to have here the sine that's going to be in common, and then here will be the cosine of phi minus I times the sine of phi. That's going to get me what's up in here. So this sine is going to be there, and then that cosine is here, and then this sine is there with the minus I that goes with it. The next one down here would be the similar trick, but just I have a plus I. So it's the same thing, same trick down here, but it's a plus I. And then down in this lower right is a minus cosine of theta. Now, neat thing about this is that this is e to the I phi, and this one here would be with the minus sign. So I have n dot the Pauli matrix vector is cosine of theta, sine of theta, e to the minus I phi, and then here sine of theta, e to the I phi, and then here a minus cosine of theta. That's kind of nice. And now what I would like to do is I would like to find what the eigenvalues are. So I take this operator, and we're going to operate on C1, C2. Remember our regular approach here, cosine theta. Just copy this again, like that. And this is the sine of theta, e to the I phi, just copying. And this is going to be then C1, C2, and this has to give me the same thing back. I want to find what the eigenvalues are. Like, we did one of these before, where remember we did the sigma x1, and we found eigenvalues like 1 over square root of 2, 1, 1, and 1 over square root of 2, 1 minus 1. Well, I'm just doing it in general now. This is like in general direction. If you want the x1, just make this point in the x direction like an I had, then you would get the x1. So I'm doing them all. And actually doing the z1 too, just doing everything. This is kind of a neat little mathematical review of a lot of stuff. Okay, so now remember the trick? What we do is we take the determinant, we have the cosine of theta, we put a minus lambda there. The determinant here, we subtract, remember we go ahead and subtract this, and we did this before, we had the minus lambda here along the diagonal. And here you would have a minus lambda. So that's just like we did before when we were doing the case with sigma x. We had a 0 here. We had here then a 1 up there and a 1 there. So when we did that case, you know, we had this situation like that, then we had a minus lambda, 1, 1 minus lambda. Remember, we did that one earlier. So this is like this is the generalization. If you have the x direction, you would have, this would reduce, in other words, the x direction. In the x direction here, you want the theta to be 90. So if theta is 90, it's gone. And then the sine of 90 is 1. And then for the x, you want the phi to be 0. You want to go along the x direction, so you want the phi to be 0. So like you would get this. You know, and if you want to do the z one, the one that's going up here for z, you want theta to be 0. Well, if theta is 0, then you would have a 1 there, and then you would have a 0 there, and you would have a minus 1 there. But see, that's what you would get if you had this one here with the 1, 0, 0 minus 1, and you subtracted lambdas, you would have 1 minus lambda, minus 1 minus lambda, and these would be zeros. So we're doing a general case. So therefore, this is going to be, multiply this to get the determinant. This is going to be minus cosine squared. This is actually sum and difference. So if I put the minus sign out here, then this is like having the cosine of theta minus lambda and the cosine of theta plus lambda. And then I'm going to subtract this one. These exponentials go away. So this is going to be just sine squared theta. And this is then the difference, say, squares, cosine squared minus lambda squared. That's cool. So got a really nice equation here. We have minus the cosine squared theta plus lambda squared minus sine squared theta equals 0. And that means lambda squared equals cosine squared theta plus sine squared theta, which is 1. Oh, that's wild. Look at that. In a general case, we're getting a similar result at the eigenvalues plus and minus 1, which is cool. Very nice. So now we want to find the eigenvectors in the general case. So the lambda, if it's plus 1, that's going to be the eigenvector. We'll call that with the spin up for our new direction here in general. And when the minus 1, we can call that some chi would spin down. So now we're ready to do it. We're ready to do it. In other words, the cosine of theta, sine of theta, e to the minus I phi. Okay, this is the matrix that we had. When you operate, say, in A and B, we'll call that A and B instead of C1 and C2. That has to get you back A and B. And just so you know that this reminder, this is the operator that we're using. This is the n dot sigma operator. Same thing. Now it's time to do the math. So here, if you multiply this out, you'll get cosine theta times A plus this stuff times B. So B times the sine of theta, e to the minus I phi. And then here you'll have this stuff times A sine of theta, e to the I phi. And then you'll have this stuff, because you're taking that sideways, times B, like that. And that has to equal A and B, like that. So that means A cosine theta plus the B sine of theta, e to the minus I phi, has to equal A. And this tells us, if we look at this thing, this tells us that B sine of theta, e to the minus I phi, is equal to, if I subtract this, this is a 1 minus cosine theta. And that means b over a would be equal to 1 minus cosine of theta over the sine of theta. Divide by this, it'll change the sign if I want to bring it up in the numerator. Okay, now it's time for some trig. And here, I'm going to refer to the book here to show you that we have everything, we can derive everything. So we have derived these equations earlier in our course from the rotation matrix. And if you make them the same, alpha and beta, then you get these cool equations. And what I'm interested in here is I'm interested in the equation where I'm going to use, what I want to use is I want to use this one. All right. So yes, we would look that up, or you would remember that, but it turns out that this little review in the book shows you how to derive it. We derive these with the rotation matrix. Then here you get this one if you put alpha equal beta equal theta. And then for this one, you are basically noticing that this is double the angle. If that's the angle, then these are half the angle. So you get that formula. And I would like to use that, see, down in here. Also, I would like to use this equation here, which shows you here how you can get it by making the alpha equal beta, then the cosine of 2 theta, similar one. So you get these two, because I'm going to use that one in, I'm going to say 1 minus that one for the top one here. Okay, so if we do that, then what we're saying here is that we're looking at these identities, which are derived in the book for you. So we really don't have to look them up. We're looking at this one, and we're looking at this one. It's going to be here, where this one here is the cosine squared theta over 2 minus the sine squared theta over 2. So that's in the book, the derivation, and then we're going to write this as 1 minus cosine squared theta over 2, and the minus will give you a plus sign here, sine squared theta over 2. All right, so trig identities. Notice that this first piece here is going to be sine squared theta over 2. So this is the same as 2 sine squared theta over 2. Okay, now it's time to put all this together. So b over a is the 1 minus cosine theta is going to be this. So we put this up in the top. And then down below, we want the sine of theta, and that's this one here. And then this last piece goes there. So now what we can see is that we got cancellation here where one of the signs are going to go out. So this is going to get you here the sine theta over 2 divided by the cosine of theta over 2 e to the I phi. So what I'm going to pick here, remember we have normalization, but I'm going to pick, we'll check with normalization. I'm going to pick that the A is the bottom one, like this, and the B is the top one with the exponential going with it. And then I'm going to check, remember we said for normalization we went A star plus B star to be 1. And here, if we do this, we'll get the cosine squared theta over 2 for the first part, plus this one's going to be sine squared theta over 2, but then this is going to get you E I phi, E minus I phi when you do the star for the second part is going to be 1, and this is going to be 1. So this is okay. We are normalized. So therefore, the answer is, for the spin up, we got the cosine of theta over 2, and we have here e to the I phi, the sine of theta over 2. That's what we get. And then we could ask, what does it all mean? Well, let's look at our system here, x, y, and z. Come out here, just reproduce what we had before, the rho, the phi, and the angle theta. And this is your general direction, like this. If I wanted the direction to be k hat, then I would want the theta to be 0 degrees. So if theta is 0, then cosine of 0 is 1, sine of 0 is 0. So that would get me, for the up, 1, 0. And then here, sine of 0 is 0, cosine 0 is 1. And I would get what I expect for the z component. Now, if we were to look at the I hat, which is one that we did for the x, then we would want to have theta to be 90 and phi here to be along x to be 0. And then this would be, say, 90. This is wild. You're going to have cosine 90 over 2, which is the cosine of 45, which is radical 2 over 2, which is 1 over radical 2. And then this e to the 0 is a 1, and that's the sine. You get the same thing, and you might recall that for the x direction, we had a 1, 1. We called it u, 1 over square root of 2. We got that. And then we called the down one. We got the down one. We had this. Now, if you put in over here, you're going to get the minus sign. You're actually going to get the minus sign up here and a plus sign there. But the main thing is that the signs are opposite. Overall phase is not a problem. That's what we call that, an overall phase. When you get probabilities, you square things anyway. So, but that checks out. That's good. Now, another thing to look at is what they call orthogonality. If you take, for example, the U dagger, what you do is you just swap these and make a row instead of a column. And then if you did U dagger U, you would have here 1 over the square root of 2 would be squared. You'd have 1, 1, and 1, 1. And this would be 1 plus 1 is 2. And this is 1/2, this is 1, this is normalized. And then if you did U dagger V, you would have the 1 over square root of a 2 squared, you'd have this 1, 1, but then you'd have the one with the minus 1, and you turn that sideways, you get 0. So these are orthogonal. That's kind of cool. And in general, if you have, say, some A and B like this, for some spinor, then the dagger would be to go A star, B star, and turn sideways. And then if you hit these together and use the rules of multiplication for matrices, you turn that sideways, you get A star A plus B star B, and that's 1, that's normalization. So that's kind of cool. All right, so that helps us understand what the meaning is. And this helps us understand this up or down nature, helps us understand what we did here when we had this general case like this. What this is saying is that, remember, we did this for some general direction. say set theta, and here we have our phi. So in this direction, if we're spin up along this direction, this top gives you the probability when you do the, in other words, this top part here, if you go C1 star C1. So just think of this as in general. This is a C1, C2. So the C1, C star gives you the probability that you get an up if you were to measure along the Z. Here's the way to see this. This is equal to C1 times the up along the Z direction and the C2 times the down along the Z direction. So the probability that you're along Z, when you measure, you're measuring along Z, but you have this spin. Let's say it was just measured and you got this. But now if you're to measure along Z, you'll get this. So when you had the X case like this, let's say if we had a spin up along the X direction, remember that was 1 over the square root of 2, 1, 1. And we call that U. Now, if you want to make the measurement along the Z direction, notice that this is like smack, 90 degrees with respect to the Z direction. There's no preferred direction up or down. This says you're going to get 1/2 of the time you're going to measure this, and 1/2 of the time you're going to measure down, because you can write this as 1 over the square root of 2, 1, 0, plus 1 over the square root of 2, 0, 1. So this helps understand all the stuff that we have done. You're basically finding here the spin up along an arbitrary direction, and these here give you the probability of making the measurement along the Z direction. If you want one more example, we can take, say, theta to be 60 degrees. Okay, that's a theta to be 60 degrees. Then, for the 60 degree case, you would have here cosine of 30. All right, so if you have, say, 30 cosine, let's put down some stuff here. So for 30, you would have here the square root of 3 over 2. And then for the lower one, you'd have e to the I phi, and the sine is 1/2. So that would give you the probability, if you make the measurement along the Z, when it's lined up along this 60, you would get 3/4 of the time you would measure this, spin up along Z, and here you would have to take, this is a C2 star C2 for the bottom one. The exponential, when you put the stars and get you the minus sign up there, it's going to go away. So you're just simply going to get 1/4 for this case, which makes sense since the total probability is going to be 1. So that's the insight as to what we're doing. Now for a Feynman observation. If you go 360 on this thing, then when you take 360 divided by 2, you get cosine of 180, you get a minus sign. You don't get the same thing back. So if you do 720, you actually get the same thing back, because that's theta over 2 would be 360 for the 720. So you do have this little phase stuff coming into play, which is kind of interesting. And the Feynman trick is to do what the waiter does, to get the same thing back. You basically are going to go around twice. The waiter, very nice. Kind of weird, these spinors. Okay, and the last thing here is the Paulie equation. And what Pauli did here is make the wave function become a spinor with two functions with respect to xa. And then your Schrodinger equation, he's putting in spin by hand. So you would have then the spinor since the electron has the spin, like that, then this potential could be in general a little matrix here, a 2 by 2 matrix that have spin interactions. And then here you would imply that there is a unit identity matrix here. So you have a matrix equation. And then the Hamiltonian, in this case, is minus h bar squared over 2m. The identity matrix times the derivative piece, and then the potential energy would have then the matrix. And that's putting in spin by hand. Wolfgang Pauli, the Pauli effect, the theoretical physicist, incompetent in the laboratory. Things break if he even shows up. So that's the famous Pauli effect, that if Pauli shows up, your experiment won't work. And one time an experiment didn't work and they found that Pauli was at the train station in the town. This is sort of the idea that the theorist walks into the lab when the experimentalist is working, and the equipment starts to break or malfunction just by the mere presence of the theorist, the Pauli effect. And then here the famous put down, not only is it not right, it's not even wrong. And then Pauli, tough on a student in class. One day he said something was trivial, and the student said, asked a question, didn't see it, and then Pauli went away into his office and did a calculation on his own blackboard, came back or said, or in his notes, and came back and said, it is trivial. You wouldn't be able to get a job at UNCA if you did that. And then here, Max Born comment on his assistant Pauli. Since the time when he was assistant in Göttingen, I knew he was a genius, comparable only to Einstein himself. Wolfgang Pauli. And with the Paulie equation, this is putting things in by hand. This is not as elegant as what we'll find with the Dirac equation, where we'll see the spin arrive naturally in our next class.